In the real world, we can model the cost of filling up this gas tank with a simple linear equation. If the fuel costs $2.75 a gallon, the total cost is y equals 2.75x. But mathematics on paper ignores physical constraints. You cannot pump a negative amount of gasoline, and if the tank has a maximum capacity of 15 gallons, you cannot pump 20. On a coordinate plane, the line for y equals 2.75x extends infinitely in both directions. In reality, that line is chopped down to a specific, usable segment starting at 0 and ending exactly at 15. To truly understand any mathematical relationship, we have to map the exact boundaries between theoretical infinity and actual reality. We define these boundaries using three foundational terms. First is the domain, the absolute set of all valid input x values. These pass through the function into the codomain, the broad target universe of potential outputs. The smaller footprint of actual y value outputs produced is the range. Because a function requires a defined output for every input, any number that results in a mathematical impossibility effectively falls outside the function's territory. When you look at a raw equation, the baseline assumption is that the domain includes all real numbers. You assume infinity, and then you check to see if any specific rules restrict it. There are three major constraints. First, if you have a rational function, which is a division of two expressions, the denominator can never equal 0. If you try to input a 1 into the function 1 over x minus 1, the math fails. Second, you have square roots. It is mathematically impossible to input a negative number into an even root and yield a real result. Third, logarithms require inputs to be strictly greater than 0. A logarithmic function hits a hard mathematical barrier if you try to input 0 or any negative number. Calculating a domain is a process of elimination. You start with the entire number line and remove the specific values that cause the equation to fail. If the domain is the set of inputs allowing an equation to function, the range is the set of outputs those inputs can actually reach. To find this algebraically, we solve the equation for x to see the relationship from the perspective of the output. By isolating x, we can treat the y values like inputs. If a specific value for y makes it impossible to calculate a real value for x due to a 0 in the denominator or a negative under a root, then that y value is excluded from our range. We record these discoveries using interval notation. This is the standardized mathematical syntax used to write out exact boundaries. The punctuation specifies the type of boundary. We use parentheses to denote exclusive endpoints, boundaries the function approaches but cannot touch. We use square brackets for inclusive endpoints, denoting a solid boundary the function actually reaches. Interval notation acts as a precise contract for a function, dictating the numerical territory where the equation is permitted to exist. Algebra gives us invisible rules, but mapping a function onto a coordinate plane provides visible evidence. We can find the domain graphically by looking at where the curve covers the x-axis. If this graph is squished vertically until it lies perfectly flat against the horizontal line, that resulting footprint is the domain. We can find the range the exact same way. If we compress the curve horizontally against the y-axis, the resulting vertical footprint represents every output value the function successfully produces. The algebraic restrictions we calculated earlier, like dividing by 0, physically manifest on this grid as visible holes in the line, sudden vertical jumps, or infinite asymptotes. A graph acts as a truth serum for a function, translating hidden algebraic constraints into undeniable physical shapes. The ultimate test of these boundaries is the piecewise function. This is a single function stitched together from multiple different equations, each operating over distinct, separate intervals. To navigate the jumps and discontinuities, you match the visual endpoints to your interval notation. An open circle indicates an exclusive boundary, needing a parenthesis. A closed, solid circle indicates an inclusive boundary, requiring a bracket. To calculate the total domain and range for the entire function, you identify the footprints of each individual segment, and then stitch them together mathematically using the union symbol. By mastering these boundaries through algebra and geometry, we can look at any mathematical relationship and see a defined territory with clear, predictable limits.